Yeah, so hi everyone, welcome to the Umbrellas webinar. I'll be doing a short introduction and then I'll give Mitzi the microphone and the video for her talk, and then we will open up for question and answer. However, if you have any questions in the middle of the talk, please feel free to write it in the chat so that you don't forget it, and then Mitzi will answer them. This webinar will also be recorded and it will be available on our YouTube channel in the next 24 to 48 hours. A little bit about Data Umbrella. We are a community for underrepresented persons in data science, and we're a nonprofit organization. Our team, so we have Reshma, whom you have just seen. She's a statistician and data scientist, and you can find her on Twitter, LinkedIn, and GitHub as Reshma S. I am Beryl Kanali. I'm a statistician and data scientist as well. You can find me on Twitter and GitHub as Beryl Kanali. We also have a code of conduct, and we thank you for helping make this a welcoming, friendly community for all. How you can support us, or you can support us by following our code of conduct so that everyone feels welcomed. And then we have a Discord community chat where you can join and ask or answer general questions, share events, jobs, and any other related material. You can also donate to us. We are on Open Collective as Data Umbrella. We are also on Benevity, which is a company matched enabled platform where, for example, if you donate $100, your company matches the same donation. We have a YouTube channel as Data Umbrella where we post videos to all the webinars we've had. So if you want related videos to do with data science, machine learning, career development, you can find them on our Data Umbrella YouTube channel. We have several videos that might interest you. So we have a playlist on career advice, which is generally advice on data science and tech as general. We also have other playlists like data visualization, contributing to open source, scikit-learn, PyMC, and NumPy. We also have a monthly newsletter on Substack as Data Umbrella. You can sign up to our newsletter, and we always send out a monthly newsletter, so we won't spam you. So feel free to sign up so that you can find out our events and get access to quite interesting blogs. We have resources on our website. Our website is dataumbrella.org, where you can find list of conferences, material on open source, accessibility and responsibility, AI ethics, and many more. We are on all social media platforms as Data Umbrella. You can find us on Twitter, LinkedIn, Facebook, and Instagram. You can also join our Meetup group where we post all our events. We usually have at least 2 events per month. We also have a job board. If you're interested in tech and data science related jobs, you can view our job board on our website. We have a live captioning for this webinar. If you go to your screen on the right, you'll find a button for live captioning. Feel free to use it if you need it. We call for volunteers to help us with adding timestamps. So if you feel that this talk is very interesting to you, you can go to our GitHub and then pick an issue and work on the timestamps. So we have a timestamp issue. You can just reference the exact event or the exact video. It does not have to be this events video. We have several other videos that also need timestamps, so feel free to go to our GitHub and check them out. We have several upcoming events. The next event for this month will be software testing in open source software and data science. And we have a September 8th event on how to build a personal brand with your customer in mind. Today's talk is on software engineering for probabilistic programming. And our speaker is Mitzi Morris. Mitzi is a member of the Stan development team. As a software engineer, she has contributed to the core Stan C++ infrastructure and authored Command Standby. As a Bayesian analyst, she has helped epidemiologists use Bayesian methods for disease mapping, and her background is software engineering and natural language processing with a detour for genomics and bioinformatics. You can find her on GitHub as Mitzi Morris. With that, I will now hand over the mic and the video to Mitzi so that she can start the webinar. As a reminder, please, when you have a question, drop them in the chat and then Mitzi will get to them and answer all of them. Thank you. Mitzi.
Okay, we are ready to go. Without further ado, software engineering for probabilistic programming. Hello, everyone. Thank you for bearing with me through the obligatory technical difficulties. My name is Mitzi Morris. I'm a member of the Stan development team, as you just heard all about me. And today I want to talk about software engineering for probabilistic programming. So, software engineering, what is it? Software engineering's been around pretty much as long as people have been trying to write big software systems that actually go into production. So software engineering took off in the 1970s at the point where companies like IBM or the rest of the large nascent software industry realized that they were having a terrible time getting the next version of their software out there. So they ran into all sorts of problems and they developed what they called an engineering discipline, which is really an attempt to get in control, to keep on top of the challenge of building a quality software system. And by quality, we mean usability. Usability is first. These things that are listed here under quality, these bullets, are in fact, to my way of thinking, they are the priorities. It has to be usable. It has to be stable. Then maintainability is something that you, as the software developer, need, especially if you're a company trying to sell a product and continually improve it. Last is efficiency and scalability. And all of these things involve massive amounts of trade-offs and pushing bumps around under the rug. But the way to do a good job on this is, there's no magic bullet, but designing, documenting, and testing. And all of these activities are activities where you step away from the keyboard in as much as you step away from the programming itself. You stop trying to keep coding. You stop trying to build more stuff. You step back, you take a good look at what you've got, and you think about it. And testing is a huge part of development, but so is design and so is documentation. All of these three activities are as important as the ability to write good, clean, efficient code. For probabilistic programming, what are we doing in a probabilistic program? Well, a probabilistic program is a description. It's an explicit description of what we think the data generating process is. So we come up with a box and we put labels on all of the components, and these are the parameters of our model, or they're the data that go into our model, and we've got a process which we believe has generated the data that we have that we want to analyze. So we build a probabilistic program, and the inference engine is going to take the data, and from the data, it's going to infer the parameters. So we say that what we're doing, what inference is solving the inverse problem. If this is the data, what are the parameters that went into the model that generated that data? And probabilistic programming is in use already everywhere. And it's doing your testing. It's running your every kind of test where you've got people taking tests, and there's some algorithm that is trying to infer how well somebody knows a subject based on how well they did on a particular test, how well they will do in the future based on how they did on a particular test. And then all over the world of sports and every kind of activity, we want to get player ability, team ability. And there we have a lot of data on past performance. Clinical trial data is a huge place for probabilistic programming, because we do have very specific models of how the body absorbs and how the body gets rid of drugs. And so we want to know, given all of these constraints, how well a drug is likely to do in the general population. And developing drugs and testing drugs is extremely expensive. So these things matter a lot, getting the right answer. And then, of course, in the public health, since COVID, estimating what's going on with a disease based on the amount of tests you can get from a non-random sample of individuals, and then, of course, election outcomes from voter surveys and census data, and every other kind of trying to infer public sentiment based on surveys. So probabilistic programs are very widely used pretty much everywhere. And it matters that you have a program that does what you think it does, and most importantly, it matters whether or not you're doing good predictions or doing fair predictions. So software engineering for probabilistic programming is just the activity of trying to develop and maintain quality probabilistic programs. And by quality, we mean the same thing for a probabilistic program as we mean for other software systems, and the same best practices apply. But let's make this concrete. What do we really mean when we say design a probabilistic program, document a probabilistic program, test a probabilistic program? Because what does a probabilistic programming do? What does a probabilistic program do? It takes some data and it makes some predictions. So how do you actually test that? And the tools that we have are simulation and data visualization. And most of today's talk is really about the importance of data visualization and the importance of design and testing to improve your probabilistic programs, your statistical models. So the example here is taken from chapter 12 of Data Analysis Using Regression and Multilevel Hierarchical Models by Andrew Gelman, who's my boss, and Jennifer Hill, who's a professor of statistics at NYU. And they have the Radon chapter 12 of this book is about doing what's known as multi-level Bayesian models. And the radon data is about a study that was done by the EPA in the 1990s about how radon gas is present in the homes across America. So radon is really bad, especially if you're a smoker, but it's also really, really, really easy to ameliorate. It builds up in basements because radon is seeping into your homes from the ground because the soil contains uranium. Uranium is a radioactive mineral, and as it decays, it releases radioactive byproducts, and one of those radioactive byproducts is radon gas, and radon gas gets into your home, and if you just open the window or put in a fan, you can get it out of your home. So why don't we just do this? Well, we are going to use that example, and the first thing that we're going to do is we're going to do a lot of preliminary data analysis. Because what people forget when they're building statistical models is that the estimates and predictions that you're making are the results of conditioning the model on the data. So people get into really fancy models because fancy's got to be good. It's got to be smarter and better than what the last guy did. But what is your data? That's really what people overlook time and again. And I'm really speaking from experience here where I've watched people march into this, and you got to know your data. So let's ask some basic questions. What do we want to estimate? What data is available? What are its shapes and tendencies? So for this study, we want to know how much radon is likely to be present in a home if we know where the home is located and whether or not it has a basement. And the chapter 12 of Gelman and Hill confines their analysis to Minnesota. And so my talk today is just going through the book and checking the work of my boss, which is really a lot of fun. And what we've got two kinds of data. We've got data, which is the individual houses that were measured for this study. And for those homes, we know what floor the measurement was taken on, and we presume that that indicates whether or not the house has a basement. And floor 0 is the basement, and floor 1 is the ground floor. So we assume that most houses, if there's a measurement for them, and also we assume that we only have one measurement per house. I asked Andrew about this, and he said, well, I'm really not sure, but let's just say we do. So first thing, getting back to know your data, we're taking some data and we're still not really sure what's in our data set, so we better start checking. At the county level, we have a list of the soil uranium levels for every county in the United States. And so we've put both the radon measurement and the uranium measurements on the log scale because this lets us work with everything additively, and that's kind of key. So we're just going to have log radon and log uranium measures here. This is how the data is analyzed in Gelman and Hill. It's going to help us check their work and keep us on track. What we need to do in order to model this data is we need to make sure that the counties line up between the table of home radon measurements and the table of county level measurements. And the other thing that we're also very interested in is for every county, how many measurements do we actually have? So you see in the county level measurements table, we have the number of homes. That's the number of homes in the EPA radon study for that county. And that's about all we have here. So we can do some very simple counts. Start simple, count the data. There's 919 homes that were measured for Minnesota. There are 85 counties. And if we look at what the distribution of the log radon levels are, it's got a mean of 1.2, which means absolutely nothing, and it has a pretty wide standard deviation. The minimum number here minus 2.3, great. There were a few houses in the study which said that they had a 0 radon level. So we made that to be a 0.1 radon level, and then we log transform it, and it came out to be minus 2.3. We believe that there's always radon present because there's soil and there's some uranium in the soil. So when you're taking a measurement of the radon, we expect to see a positive number there. When we work with the data here, we had to do a little data cleaning on the inside. So again, always be aware of everything that you've done to your data on the way into your analysis. And the first thing that we want to see is, okay, what's the distribution of our radon measurements? And we can do this in plot 9 using a density plot. Somebody said they lost their audio?
I can hear you. I think you're good.
Oh, good. Okay, so density plot, and what you want to look at on the y-axis here is that the density plot is the highest point of the y-axis is only 0.5. So this means that this density plot here is in fact very diffuse. There's not a lot of a one point that shows up as your central tendency in your log radon level. And we can use plot 9. So a lot of this talk is about the importance of doing good visualizations. And I have to say that when you're working in Python, you really do want to learn the plot 9 package because it gives you a very beautiful way of layering information onto a plot in a systematic way. So here what I have are 3 layers where each layer is a different density plot. And I've got the basement is in orange, the ground floor is in violet, and here's a dotted line showing you what the undifferentiated density is if you just put all of the data together. And what we're seeing here is, gosh, this blue dotted line sure looks a lot like the basement orange line. And well, that raises the question of, hey, what's going on? And what's going on is if we just plot the raw number of observations, what we see is almost all of the data is coming from the basement. And in fact, if we go and use pandas and crunch the number, the basement level accounts for 83% of the data, and we only have 17% of our measurements taken from the ground floor. So if we're trying to say, well, how much of an effect does taking a measurement on a ground floor versus the basement do, we don't have as much information about what happens on the ground floor. Just a thing to keep in mind when we're going to start building our model. And the other thing is that our goal is to say, well, we know what floor whether the house has a basement, or a ground floor, and we want to know the county that the house is located in. These are what we're going to use to predict what the average radon or the expected radon level for that house is going to be. Well, again, how many counties have data from both floors? And that's about 70% of the counties have measurements from both floors. And then the next question is, okay, so for a county, how many observations do we have? And this is a histogram where the y-axis is the count of the number of counties that have the x-axis number of observations. And it's not a very good plot. It's kind of difficult to put your head around what this means. So let's do a different plot. Why don't we plot on the y-axis the soil log uranium level, And then on the x-axis, we'll plot how many homes there are in that county. This lets you see that we have a few counties, which are metropolitan areas, which do have a fairly large, a certain amount of data, more than 100 data points in 2 places, and more than 25 data points in another 4 places. Everybody else, we have almost no data. And this is kind of concerning because if we look in this upper left-hand area, we've got lots and lots of counties where there's a fairly high or a relatively high soil uranium level. And we would think that that's going to make a difference, but we're not going to have a lot of data. And when we do a plot which tries to say, okay, this plot's a little bit complicated. What this plot is doing is we're taking a visual summary of all of the data points that we have for each county, and we're arranging them in order of the county level soil uranium. High is on the left and low is on the right. And this plot, I think, should be fairly familiar. Statisticians, data scientists love these box plots. They're called a box and whisker plot. And what we're showing with this plot is we're showing the central 50% of the data is in the box. There's a heavy notch for the median point in your data. You have whiskers, which go out, I think, about 1 or 2 standard deviations. So they cover the central 95% of the measurements. And then anything that's deemed too far away is an outlier. And so we have a few outliers, and we've plotted them using plot 9. And we've also made the width of the box be variable, so it's proportional to the square root of the number of observations. So again, we see that we have a few counties with a lot of data, and they don't have relatively high, the soil uranium for those counties is not all that high. And then for all these counties where we'd love to know what's going on, is the soil uranium level very high? Well, the measurements are so diffuse and so sparse, we don't really know what's going on. So just to summarize what we've seen already, the range of radon measurements is very wide. We have noisy data. Most of the measurements are taken on the basement level because we assume that in Minnesota, the houses tend to have basements. And we don't have basement ground floor observations for a lot of counties. And the data that we have follows the population density. So we have about 8 metropolitan areas where we get over half of the observations. So most of the population of Minnesota is going to live in a metropolitan area, not in a rural county. And we also know that according to the way that we've seen, there is variation across the counties for the soil uranium levels, but we don't have a lot of data for counties with high soil uranium levels. And I don't think that has that much to do with why those counties are populated because, but I don't know. I really don't know anything about geology or geography. We've got data. We now know a little bit about that data, and this is going to help us understand what our model's doing because we're conditioning our model on the data. So for model building and model testing, what we want to do is we want to systematically test the model predictions. And there are 2 workhorses of model testing where you're just testing, does this model do what I think it's doing? And one of those is prior predictive checking. And this is about what your model will do if you didn't give it any data whatsoever. And this is a quite sensible question to ask because there are always assumptions cooked into a model. And without any data, we need to know what the assumptions are in order to understand how that's going to interact with the data that we actually will get at some future point. Posterior predictive checking is really the first check that goes on, because when we're building a model, we're usually testing our model on some data, whether it's a simulated data set or a sample data set or a historical data set. Usually we've got data, we run the model on the data. The posterior predictive check is the easiest and the most automatic and the first check that you should do once you've got your model up and running. Now, I'm going to do a quick review of statistics just so that we can get to showing the models. This is a terminology review. We consistently try to talk about data as Y, and actually Y is the modeled data. Y is the data that we're using as the outcome, and we're building a model to predict Y. We also have data X, which is the unmodeled data. That's the data that we use to feed into the data generating process to get out Y, which is our modeled data. We tend to use theta or any Greek letter for parameters, and we're estimating the joint probability distribution of the data and the parameters. We have to feed both of these into the model. And before we see any data, we have the prior probability distribution. That's just what we think the probability of theta is. And then once we've fit our model, conditioned our model on the data, we now have the probability of the posterior probability distribution, which is the probability of the parameters given the data. And finally, we have the probability of the data given the parameters. So if you know the parameters, you plug in the x's, you get out the y. And according to your probability of theta, according to the value of theta, which is your probability distribution. And when y is fixed, this is your likelihood. And when theta is fixed, this is your sampling distribution. So in Bayesian estimation, let's put it all together. What we're trying to do is we are trying to build a model which specifies prior and specifies the likelihood, and then we are going to estimate the posterior probability of theta given our data. So we're using Bayes' rule of conditional probability, which relates conditional probability and joint probability. So quick review, if you're confused by this, don't worry about it. And if you're not confused by this, great. We've spent enough time on this as it is. Linear regression is really the workhorse of statistical modeling. Almost everything that we're doing when we're doing any kind of estimation, underlyingly is some kind of a regression model, setting aside deep learning, which is also a kind of regression model. But in a linear regression, what we want to do is we want to find the linear function, that is to say, addition, not multiplication, for the straight line, the plane, the hyperplane, which is going to give you the best fit of your outcome variable y to one or more predictors x. And what we mean by best fit has a very precise very precise definition. That is, we're going to plot everything XY, XYZ scatter plot, multidimensional scatter plot, and then we're going to fit that line, that plane, through our cloud of data points. And we want to minimize the distance from the y coordinate to the plane. And this is what we're calling ordinary least squares regression. And so we have a metric. The set of parameters which gives you the best fit is the one that puts the plane closest on average to all of the y coordinates in your all of the y's in your data set. And so how we can write this is that because we're fitting a line or a plane or whatever, we have a line is defined by the intercept and the slope. And so again, we're going to use the Greek letter alpha for the intercept and the Greek letter beta for the slope. And when we say that the outcome is just the fitted line plus some random noise, that's all the noise is coming from the same distribution. So there's some amount of error, but the noise is white noise. It's got a normal distribution centered at 0 with a standard deviation that we don't know, sigma. And that's really the whole story, except that in this formula here, I'm being quite sloppy with my notation. Beta can be a whole vector of slopes of weights as you go into higher dimensions, in which case X is your whole vector of predictors. And usually for a regression model, of course, you're putting in as many predictors as you can find lying around. And in Stan, it's a domain-specific programming language. It looks a little bit like Java. It does not look that much like Python, but you've got named blocks. You declare your variable and you declare your input data in the data block. You declare your model parameters in the parameters block, and then in the model block, this is the specification of the likelihood. And what it says is that we think that y is distributed normally centered at our regression line formula with a certain amount of standard deviation, a certain amount of variance, and the variance is sigma. And the variance sigma is actually, that's actually sigma squared. When we're talking standard deviation is sigma. So here, when we're computing with in Stan, we're always actually calculating the variance. So this is your sigma squared term. And for the log radon data, we're going to develop a regression model. And we just say that, okay, the observed log radon is going to be some offset from 0 and some effect of what floor the measurement was taken on with a certain amount of unexpected variance. Now, because we're coding floors as 0 for basement and 1 for the ground floor, what this really means is that if you're on the basement, your log radon is just some alpha, some offset plus noise. And what Gelman and Hill chapter 12 is all about is building a multi-level regression. And multi-level regressions allow you to model the dependency structures in the data, as well as modeling the relationship between the outcome and the predictors. And what this does for you is that it gives you a partial pooling of information across members of the data set which share structure. So houses are located within counties, and we can say, okay, either all the counties are absolutely unique, they are all special snowflakes, or we can say that all counties have some amount of similarity. At the point where we want to say that counties are somewhat alike, what we need to do is we need to put a common distribution. And if counties are more or less alike, well, great. We can put a normal distribution. We can say that they have mean and they have a variance. So in a multi-level model, all we have to do is we have to take our regression model here, which says we have the log radon is distributed normally based on the county you're in and the floor you're on, and there's a certain amount of variance. And then your counties all have a certain baseline value and a certain amount of variance. So we have two sources of variance. We have the individual level log rate, the individual observation variance for the whole model sigma, and that's just one variance term for all of the observations. And then we have another variance, sigma alpha, which is the variance term for the distribution on the counties. So multi-level models are insanely powerful. And in a multi-level radon model, in STAN or in any other probabilistic programming language, we're going to have to specify the data, the number of houses, the number of counties, the log radon measurements, and the floors that the measurement was taken on. And then for every measurement, we also add a value, which says this is the county that I was located in. And then what we're going to estimate is we're going to estimate for every county the alpha, a vector of per county intercept terms, and we're going to have j of them. And then we're going to put a distribution on alpha. So we will have mu alpha and mu sigma, which are the mean and variance for that distribution on alpha. Then we have beta, the coefficient of the floor level, that's the slope of the line. And then we have sigma, the common variance term. That's our entire model. And I can show you what the in the STAN program, how we write just the model. This is our likelihood. This is the prior on our alpha term. And these are priors on all the other terms in the model. In the alternative where we say all counties are different, it looks almost the same. There should be a prior on alpha that would look just like the prior on beta, and we would have an unmodeled vector of alpha intercepts of size j, and we would have alpha, this indicator value, and STAN's notation, which we're going to skip over here because writing STAN programs is learning a programming language, and that's more explanation than we've got time for. So let's just skip straight to the model comparison. What I've done in plot 9 is I've got two different plots which are overlaid. The blue plot is the estimate from the multi-level model where we've done some partial pooling. So what we're showing you is for every county on the x-axis, all the counties here, what these segments are showing you are the upper and lower bounds of the estimate for alpha, the county level intercept. So this is within one standard deviation of our estimate of the intercept, and this is ordered by how much data we have for each county. And what you can see happening, and the blue line here, this is the estimate for the multi-level model. This is our mu alpha. This is what we think the average county intercept is, a net average. This is what we think the generating distribution, that distribution we put on the alphas with normal mu alpha and mu sigma. This is mu alpha, what the mean for that distribution is going to be, and it's going to have certain amount of variance, which is mu sigma, which we haven't shown here. And the orange estimates are the same things for the no pooling model. That is, every county has its own intercept that we estimate from the data. And what you see across this chart is that the more data you have, the tighter your estimates get, and that there is definitely, for the multi-level model, you are pulling all of the estimates towards the central mu alpha, and also you're giving yourself a much tighter estimate of what that is. So this is the fundamental demonstration of why you need to do multi-level modeling, because in so many cases, there is structure in your data, and you need to model that structure. And the Bayesian framework gives you a perfectly flexible and perfectly coherent way to express that. That's very natural, and it tells you what you want to know. And so finally, we're going to look at the posterior predictive check. And the posterior predictive check, said by an insanely wise statistician at Columbia named Ben Goodrich, is that you just take your estimates from your model and your data, and you generate a whole new data set. And every time you run the MCMC sampler, which we haven't even talked about, we get a new data set. So we're using Monte Carlo Markov chain MCMC methods to estimate our parameters from the data. It's an iterative process. At each iteration, we get an estimate of what we think our parameter values are. And at every iteration, we take that estimate, plug it into this formula, and get a whole replicated data set. So what we can do then is, with the statistics on the replicated data set, we can compare them to the statistics on Y. And this is a basic check that tells you, is my model fitting my data? That's all it's saying. Is my model working? And here's a posterior predictive test where we see what the mean of our replicated data is, how that compares to the mean of the observed data. And the way to do that is to just overlay the mean from the estimate on the box plot that we showed earlier of Y. So this was the box plots that we were showing just to show you how things were going with the soil level uranium and the radon measurements. This is that same box plot, only now we just have all of our counties organized alphabetically. And we see that what we're seeing here is that, the replicated data set, the means for the replicated data set look very close for most of the counties. They look very close to what the actual data is. And another way to visualize this is to just go back and get that density plot of Y, the home radon levels, and overlay it with a random sample of the density plots from our replicated data sets. And again, we see that this model is doing a really, relatively fine job of fitting the data. So in conclusion, what we've seen is that we do data visualization, and this drives our design, our testing, and our documentation. And here we've looked at posterior predictive checks to validate the model specification. And Plot 9, I can't say enough great things about how much fun it is to build visualizations with Plot 9. The more ways you can visualize the data, the more questions that you think of, because it's going to be so much fun to visualize them. And finally, we really are, when Reshma asked me to give a talk to Data Umbrella, she said, well, would you tell people how they could contribute to the STAN project? Well, we really would love to have feedback and ideas on plots that you think would help you validate your models, validate your predictions, and just give us some confidence in the in the probabilistic programs that we've built, such that we can put them out there and say, yeah, you wanted to know what the COVID level here was? I'm telling you, and you might be mostly right. That's all we ask. So in conclusion, I would like to thank everybody. I would definitely like to thank my fellow STAN team members who helped me so much in the time I've been on the project. I'd really like to thank Reshma for inviting me, and I'd thank you for watching. So please, any questions?
Thank you, Mitzi, for the comprehensive presentation. If you have any questions, please put them in the chat or the question and answer tab, and Mitzi will answer them.
So while we wait for, while we give people a chance to ask the question, Mitzi, can you share a little bit about how you got involved with STAN?
Well, I was contributing to STAN because STAN is written, the core STAN project was started as software written in C++. So I was a Java C programmer for a long time, and I was able to start contributing to basic features of the platform. And this was in 2014 when, and the project has been going on since 2011, 2012. And the first thing I wrote was a parser to handle input data in JSON format. So, and then I continued to contribute to the C++ code base because I do have a background in building parsers and building, well, not building compilers, but close enough. So I worked on the STAN language and helped develop the STAN language. And then I got really involved in a project run by a professor at NYU who wanted to do spatial modeling of, it was epidemiology. And that led me to do a lot of modeling in STAN, and I just kept going because basically it was fun. I can say more.
Sure.
I can say more about this talk and this model. This model here that I've presented for the Radon data, the first multi-level model here, which is just having the varying intercept model. The next step for this model would
Hey, do you want to go back to that spot in the slide where the model is?
Yeah, sure. So let's go back to the data, actually. Yeah. So we can look at this or we can look at this. And quite frankly, I kind of think that, yeah, let's talk about this plot. So what's going on? We don't have a lot of data in this data set. And so building the varying intercept model, which is easy, it makes a convincing show of what putting a model, what multi-level modeling does. and it tightens up your estimates because you're doing partial pooling of information. But for this data set, what really matters is the fact that, well, radon levels come from soil uranium. So we haven't added the county level soil uranium into the model. And adding that into the model is going to be more complicated. What we would say is we would want to do the same thing for a predictor in the model, one of the beta terms in the model, as we did for the alpha. So if we look at this model here, we have now modeled the intercept term. Now we want to model the one of the predictors, beta. We would want to add in this would be beta 1 fluor, and then we would add in another term, which would be beta 2 uranium. Well, the county level uranium predictor is going to interact with the county level intercept. And computing that, you're really computing the same thing two ways. And so you're going to have to account for covariance between these two predictors. And when Andrew was writing this book, it's perfectly easy to write this model and compute this model using the existing software. When this book was written in 2006, that was our package called LME4. Or you could have used bugs. No, you couldn't. Maybe. I'm not sure about that. But there were R packages that would kind of compute this, but they would not be able to compute the point where you had a varying slope, varying intercept model. So the challenge in multi-level modeling, among the challenges in multi-level modeling, is the problem of having interactions between your higher level and your lower level terms in your model. And that's why the STAN project was started, because Andrew Gelman wrote a book where he had models that he could express, but he couldn't compute them. And for that, we now have STAN. And I would love to give a talk about the model here, which we really, really need, which is the model that adds in information about uranium. But that model actually is relatively complicated to efficiently code because there is all this covariance. Dealing with covariance in a computational setting is expensive, and it calls for a whole lot of mathematical techniques. So that's its own topic for another day. But that's just to try to, again, explain why people care about this and why people use STAN and why people need to use STAN, because this is reality, and we want to get better estimates and better predictions for, the hand we're dealt, as it were. And that's all I have to say.
I have a question. For example, if there's a beginner software who's a software engineer but a beginner, and they want to get started using STAN, what resources or where is the ideal place to start learning about STAN and finally maybe do some few projects on it?
Well, STAN is widely used. So for the beginner who wants to use STAN, the question is, okay, what's your data? What is the domain? Different domains have different problems, and they have different concerns and different ways of obtaining the data and measuring the data. There's actually common models across all domains, but they have different names. What I'm trying to get at is that if you are an ecologist, there's a lot of, I would look for STAN for ecology. If you are in sports analytics, I would look for STAN for sports analytics. STAN is pretty widely used at this point, and it's programming is very general and one size fits all, but analysis is very domain specific. It depends on domain knowledge and it depends on domain experts. So we're hoping to spread STAN competence throughout all of the branches of science, engineering, data processing, and you really need to start from your data and from your problem. And if you're asking where are the general resources, well, there's the mcstan.org site, which obviously I haven't even put on the slide, and it's my bad. We have a STAN user's guide. This is a very general reference about STAN. We have a woman named Maggie Liu who's got a YouTube channel who has some fabulous introductory videos on STAN. We have the STAN discourse forums, which have very involved questions about just about every kind of model and every kind of advanced statistical problem you would like, and a very friendly community. So you could go to discourse, mcstan.org, the discourse for mcstan.org. There's a ton of stuff out there, really. Also, Andrew Gelman's books, Andrew Gelman's blogs, everybody else's books and blogs on STAN. It's been around for a while, right? We've been around for at least 10 years. So yes, Reshma's pointer to the YouTube videos on STAN by Maggie Liu, I would start there.
Great. In case anyone has any other question, we can maybe have a minute before I stop recording. I'd said before, this webinar has been recorded and will be available on our YouTube channel in the next 24 to 48 hours. So we will also let you know, for those who have joined our Meetup group, we will send an email when the video is up so that you can go and look at it to learn more. Reshma has also shared some links on the chat. You can also add them to your resources. We also have Mitzi's presentation. We have the GitHub link. It has been pinned there. You can copy the link and use it for future reference. Thank you everyone who joined our webinar. Hopefully we will see you again, and thank you to our speaker Mitzi for such a comprehensive talk.